Today I wanted to talk to you guys about WS2811 LEDs and the variants. I've done quite a lot with these guys and I thought I would share some of the stuff I've been doing. So WS2811 is a chip from eBay from China. It's this guy, which is an LED driver. So what you've got in there is 3 constant current sinks for a red, a green and a blue channel. You've got a data in and a data out, and internally it's able to store data for its pixel, its RGB pixel, and using various different wiring arrangements we can create arrays of these pixels. So this tape is configured for 12 volts with a 12 volt variant of the chip, and it's got 3 LEDs which are all wired in series to boost up the voltage. These guys are wired for 5 volt operation, so these have a 5 volt variant of the chip and a single LED per pixel. And these are slightly different again. These are a different chip altogether. These have the chip built into the LED, and these are an SK something something. And they have a red, a green and a white channel, and that there is one white. And these have been configured as individual pixels, each on its own board, with its pads on the back for hand soldering. I only bought these just to do some testing of the chipset. You can get this chipset in other form factors as well. And these are all driven with a data interface. It's quite a simple interface really. It just has it's just based on self-clocking, which just means it doesn't have a clock. It's just one wire. It's transmit only, so there's no read back from the pixel to the micro. You're literally just sending data. And the way it works is you send a short pulse for a 0 and a long pulse for a binary 1. Each pixel takes 8 bits per colour. So these guys have, each one of these, because there's 4 colours, there's red, green and blue and white, takes 4 bytes of data, and each byte is a brightness value. So you've got 255 brightness levels, or 256 including 0 brightness levels for each pixel. So for a red, green, blue you get 24 bits of data per chip, and gives you 24.5 million colours. For RGBW pixels, it's 32 bits per pixel. You've still got your 24.5 million colours, but you've also got dedicated warm white. The arrangement is as a shift register. So you can see this tape has got our input at one end, and we have one chip, which is this section here with its 3 LEDs, then another chip with its 3 LEDs, then another chip with its 3 LEDs. And the D out of this chip goes into the D in of this chip. So, because there's no clock, all you do is you start shifting ones and zeros. So, if it was wired as red, green, blue, it would go byte-wise down the wire. You'd have RGB, RGB, RGB going down the wire. So if you sent a red, and then a green, and then a blue down the wire, they'd be shifted into this chip. Then if you send another red, then the red from this one will shift into here. Now you send a green into here, and that will shift out of there and into there. And you shift a blue into here, it will come out of there and go into there. So what you've now got is your first RGB you sent is in this pixel, and the second one you sent is in this pixel. Now you send another RGB value, and they all shuffle along the line again. And so the first one you sent is now in this pixel, then the next one's in this pixel, and the next one's in this pixel. And the more you send, the more pixels get shuffled along. Now you don't really have to worry about any of this. There's a very good software library that does it all for you, which I'll show you in a bit. But it's good to know roughly how they work. Now you can wire these things to do all sorts of stuff. So I've wired these ones as a decorative window light, which I'll show you. So here we've got ubiquitous Arduino to run it all, and then a double strip of these lights go all the way around the window like so, and I've just put a loop at this end so it goes one way and then back the other way again, Because these run on 12 volts, I've just got a 12 volt power supply running them. I've designed a few different drivers for these, a few different ways of controlling them. So these ones were a system I built as a lighting display for my wedding a couple of years ago. So that's 60 pixels with 10 centimeters in between, wired as a string of fairy lights. And on one end you've got a pigtail of wire, like so, and a 3-pin connector. I've used an XLR connector because these are super cheap on eBay. And they're fairly rugged and they can take the current. And then to control 16 strips of those, I built this guy. So this controller has 16 outputs, 8 on this side, 8 on this side. It's controlled via DMX512, but also via Wi-Fi, which I'll show you in a bit. It's actually via Bluetooth, but I did a variant of this with Wi-Fi a while back. So you've got a fan for cooling on the top, and you've got air ventilation holes, and then inside we've got the control up on the top and power supplies down here. So we have, this is a 12 volt power supply, which is slightly variable, so I've actually kicked it up to 15, just for reasons I'll go into it in a minute. That powers everything in the intermediate. These, each one of these is a 15 amp module. So this can kick out 15 amps at whatever voltage. It's a DC to DC converter. I've got 1, 2, and then space for 3 and 4 of those. I've borrowed 2 of them for a different project. And they power the outputs on the side. So these are all configured for 5.2 volts to give me a little bit of allowance for dropping the cabling. And so with 15 amps available from each module, there's the required 3 amps for each of the 4 connectors with a little bit of headroom. The intermediate voltage is, the intermediate 12 volt power supply is rated for 20 amps. And to be honest, it never draws even close to that, because it's unusual that you'll actually have red, green and blue all on at full brightness all at the same time. And in that scenario, with all 1000 pixels lit at full brightness at the same time, it would in theory exceed 20 amps at this point, but it doesn't ever actually happen, and I can control that in the software to make sure that it doesn't. So you've got your data from each of these connectors coming up through these ribbons. That's what these ribbons here are, and they go up to the Arduino, which is actually driving everything. The Arduino has a Bluetooth module attached, a DMX512 transceiver that's actually wired up so it can transmit or receive, because I did use this in one variant where it was the master of the DMX universe. So this is a DC to DC converter that is literally just controlling the speed of this fan, because going at full speed it's really noisy and it really doesn't need to go full speed, so I just put that in to drop the speed of the fan. Slight overkill, but I had a lot of them hanging around. This one provides the 5 volts that drives the Arduino. Does it? No, it doesn't. Yes, it does. So that drives the Arduino, and it just drops the voltage down a bit for the Arduino. Why did I do that? It's got its own... I think the internal regulator on the Arduino just got too hot. Then we've got the power supply and the data for the Bluetooth module as well. So that's the control side of things. Now, this is actually a really nice system to rig, because these just plug straight in here, and now they're ready to go. So you can mount that somewhere high up in a venue, preferably in the middle of the room, and just string the lights out from that point to the edges, and I'll try and insert some clips of what that can look like. So the clip you just seen was this control box driving these lights in a marquee. That was an installation that I did last December for a Christmas service at a church. You saw there was actually 2 centres for that system, which is why half of this is missing. I ended up taking 2 of these power supplies out of this box and putting them on their own little control board on the other side, running off another one of these power supplies, and that's what this grey wire is about. That's bringing 8 of the data signals out, plus a ground that was sent across to the other pillar of the marquee. And I'll insert a bit of footage now from my own wedding, showing a slightly different installation again of basically the same system. So those pictures you've just seen were from my wedding. It's the same system kind of, so it's the same LEDs, but I actually structured it slightly differently for that installation. I had 8 logical strings and 16 physical ones, and each string had an output from the centre to an edge of the room. It then went along one wall and then came back to the middle again, which simplified the control. And because they were quite long runs to be sending 5 volts for the lights, I actually sent 12 volts for the lights and had one of these blue power supply modules every 5 meters along the length of it. So there were around 20 or 30 of these in the total installation, and the whole thing ran off a 12 volt computer power supply, so it was much less integrated than this system, and it was much less professional, frankly, because I did it on a shoestring budget. So instead of using these XLR connectors, I used Molex connectors, which are hard drive power supply connectors, and going down those Molexes I had a ground, I had data for the lights, I had 12 volts and 5 volts separately, and I had them configured so that you could power the strip from 5 volts or 12 volts depending on where you supply power, essentially. But you could also daisy chain the strips and they'd pass the 12 volts along but wouldn't pass the 5, and each strip had its own power supply at the start of the module, and some of this fairly high current cable to carry the 12 volts through. Now these are the SK6812 LEDs I was talking about earlier. I'm particularly excited about these because one significant failing of these WS2811 based chips is that they don't produce a very good white. The balance between the red and the green and the blue tends to leave a fairly major gap in the yellow. It's been noted by a few other people making videos about these chips that there just isn't any light output in that kind of soft yellow, and you can tweak the balance of the red and green and blue all you like, and you're never going to get that real warm white colour that you get from an incandescent light bulb. So these SK6812 chips solve that problem by using the yellow phosphor style of LED, which is this one right here. So that's a UV LED with a yellow phosphor over the top that fluoresces warm white and gives you a really nice broad colour spectrum. So these things are really, really nice for ambient lighting, for colour effects. You can use the warm white channel to bolster reds and oranges. It does look really nice. So I want to talk now about the software we're going to use to drive these things. So we're going to use a library from Adafruit called the Neopixel library. The Adafruit guys, they sell these. They sell all sorts of different sort of test strips and products that you can build out of these. They're relatively expensive from Adafruit, especially in the UK since it's a US based company. However, you can buy these really inexpensively on eBay. So I got a panel of, and other websites as well. So I got all of these on eBay. I bought a lot of these to have 1,000 of these lights in sets of 50. I actually bought in the end I bought nearly 30 sets of these, and I did a deal with a seller and got a decent price for 30 sets, but yeah, they've lasted pretty well actually. I've had them for 3 years now, and they've been camping with me. They've been rigged in a tent. They've been rigged in several venues. They've been set up in my house. They've not been looked after, and they've lasted. There haven't been any faults with them. So to be honest, I'm pretty impressed with these. But as I say, they have this problem with yellow. I got these from Banggood. I got a panel of 100. This is what's left. I've already built a couple of projects with these now, and the panel arrived, and I think it was £12 including shipping, and it arrived within a few days, so very inexpensive. So the software that we use to drive these LEDs is the Adafruit Neopixel library, which I'll show you now. So Adafruit Neopixel is a free library you can download from GitHub. There's excellent documentation on how to install it and how to use it already. I'm not going to go into a great deal of detail about the code, to be honest, because frankly you're better off reading that stuff than watching a YouTube video. I'll just show you a very basic project here. So here's an Arduino Sketch. We've included the library. We've created a strip, and we've told it the pixel order, which in this case is red, green, blue, W for the warm white channel, which means that this is the SK6812 based chip. And we've told it how fast we want the bus to run, in this case 800 kHz, how long the strip is, which is 60 pixels, what pin it's connected to, in this case pin 2 of the Arduino, and then just initialize the library, and then we're good to go. So we've got a few effects on here where we can sort of set the color. So you know, this is just warm white. This is a color wheel, so we've got a color wheel function, which is my adaptation of Adafruit's wheel function. That's probably worth showing you. The Adafruit wheel isn't really very good. So color wheel, basis of a color wheel is simply that you have three quadrants of the wheel. You've got sort of red to green to blue, and then back to red again. And in the top it starts fully red and fades slowly to green. So in the halfway between red and green, you've got purple, I think. No, yellow. Then it goes from green to blue. So then you get your kind of turquoisey colours, and then it goes from blue to red, and that's where you get your purples. And it does a smooth fade from each one. Now the Adafruit implementation of this wheel function only has 256 steps around the wheel. Mine has 768, so you get a much smoother transition around the wheel. And this modulo wheel position max divide here simply means you can put a 16-bit integer and just have it count continuously, and it'll just go round and round and round the wheel, which simplifies the use of this function significantly. So that's quite simple. It just detects the quadrant and says either, you know, red is 255 minus position and then wheel position for green, so that just fades from red to green. So when wheel position is 0, it's red, 0, fully red, and then 0 and 0. And as it fades to 255, it becomes 0, fully green, 0 for blue. And then the same is true. It just does the exact same offsets for everything. Now, this has got a whole bunch of button debouncing in it. I'll do a separate video on button debouncing if I figure going into coding is a good thing to do. Yeah, I think that's all I'm going to do with code for now, but I'll show you a few cool things that you can make these lights do. So I can get these all in. So here are the lights that I made for my window display, and you might or may not be able to see that the light's rushing from side to side and slowly changing colour. And then when it finishes, I've got the system set up so that the pixels run in groups of 3, where the first in each group is white and the other 2 cycle through the colour wheel in a loop. And that just makes quite a nice window display that just sits and runs all the time. The white gives me some extra light at my desk, and the colours just look nice. And here's a standalone set that I made to be a bedside table lamp. These are the same LEDs as before, just wrapped around the bed with a simple 3 amp DC to DC converter, hot melt glue back to back with an Arduino. And there's a resistor in there for the data. There's also a selector diode so that the Arduino takes its power from here, but if I connect this to the computer, it doesn't try and power the lights from the computer's 5-volt power supply if I don't connect the 12 volts. This is a 12-volt input, which comes from a simple wall adapter, and then the lights are patterned to just do very light pastel colours in low brightness, which is just a nice thing to have for low intensity bedside table lamps. So here's another project I did with the SK6812 LEDs. This is a Bookcase Light, so these are the ones with the dedicated warm white channel. And I hand wired these together, stuck them around the inside of this bookcase. And these are all powered from an Arduino with a power supply down the bottom there. And this one has the 4-button based user interface with the mode button to control what colour the lights are. And that's the warm white, which, as you can see, is really nice warm shade compared with what you can usually get out of RGB LEDs. And then we've got brightness control, which the camera's correcting for. And then this wheel pattern where they're all the same colour, or another wheel pattern where we have a colour palette unrolled. So I hope you've enjoyed this little look at what you can do with these LEDs. I highly recommend going out and buying some, getting an Arduino, or even several Arduinos. I tend to buy Arduino Nanos in packs of 5, which is very handy just to build into projects. Very easy to get these up and running, especially if you've only got a few of the LEDs. It's worth noting, a string like this needs 3 amps at 5 volts, which is far more than you can pull on a USB port or pull through one of these. This does have a 5-volt output, but it's only good for 100, well, 200 or 300 milliamps maximum. So you could probably run 4 or 5 of these LEDs off of it, but no more than that. So you will need a dedicated 5-volt power supply. So you'll either want a wall adapter that outputs 5 volts. So this is a wall adapter like this, or you'll want a wall adapter that outputs a higher voltage. So this is actually a 12-volt adapter, and then something like this. This is actually a 15 amp DC to DC converter that can output an adjustable voltage, and I've adjusted it using this potentiometer here for 5 volts. It's important to do that before you connect the lights, and then you can use that to power the lights. You've got to be really careful to make sure you're never trying to power these lights from the USB port on your computer. Best case scenario, the port will just shut down. Worst case scenario, you could damage the motherboard on your computer. So that's worth noting. The other thing is, I've got a resistor between the pin of the Arduino and the first light in the chain. It doesn't really matter what it is, it just needs to be a couple of 100 ohms. And that resistor is going to stop your Arduino pin or the first light in your chain getting damaged if there's essentially when you're plugging them in. If you're hot plugging these and you plug it in with the power on, you can end up in a position where the lights try to draw their 3 amps of power through the data pin, and that fries the data pin on the Arduino. So that resistor just stops that happening, because as soon as you try and draw that current on that 100 ohm resistor, the voltage just drops to 0 and everything just switches off. So yeah, highly recommend buying some. Have a play. There's plenty of good documentation online. As you can see, there's loads of really cool projects you can do with these things.